Let us talk about phase diagrams. So this is a phase diagram for water. Phases correspond to solid, liquid, gas. And it's a diagram or a picture that tells you if they're solids, liquids, or gases. So for example, this is the phase diagram for water. This is solid, liquid, and gas. On the x-axis is temperature. And if you are at 1 atmosphere of pressure, so let's talk about pressure really quickly. Pressure is the atmospheric pressure are when molecules of the atmosphere, like nitrogen, oxygen, and so on, exert pressure on a person. So if you are at sea level, there's a certain column of air pressure on you, and at higher elevation, there's a little bit of air pressure on you, okay, because you're at higher elevation. And the air molecules are being pulled down by gravity, so it's a lot heavier or a lot more particles closer to the sea level. So at sea level, the atmospheric pressure is 1 atm, or 1 atmospheres. At a higher elevation, the atmospheric pressure is lower, let's say 0.9 atm, or atmospheres. So let's talk about only at sea level, which is 1 atm. Let's go ahead and heat up the temperature, heat up the water, and it goes solid, and you warm it up some more, it turns into liquid, and you warm it up some more, and it turns into gas. Okay, so this is an example of a phase diagram, and this is for water. You can have a phase diagram for any substance. Okay, first let's talk about some concepts here. This is a cooling curve for water, for ice. So first you're really hot, so it's a gas, and you cool it, and the gas particles are moving like this, as you can see. There are no intermolecular forces. As you hit 100 degrees, the gas will condense, and here we have two phases coexist at equilibrium. We have liquid and gas, okay? And then once all the gas is gone and condensed to liquid, the water will get colder and colder and colder until at 0 degrees Celsius, it'll freeze, and you have both solid and liquid at equilibrium. And then once all the liquid is gone, then it's just the solid getting colder and colder and colder. Okay. Just some terminology for you. When a substance is going from solid to liquid, it's called melting, liquid to gas, vaporizing, going backwards, condensation, liquid to gas to liquid, and liquid to solid is freezing. If you're going from solid straight to gas, you are not getting a liquid phase. It is called sublimation, and the opposite is called deposition. Okay, I've been using the word equilibrium, and to attain equilibrium, this is what you have to do. So you have to get water in a container, and you have to seal that water. At a certain temperature, some of the water molecules will escape as vapor. So these are water vapor. These vapor molecules are exerting pressure on the sides of the container, called water vapor pressure. Over time, you'll have more and more water vapor going to the gas, liquid going to the gas phase. Okay, at a certain time, if there's 100 of these, 100 in the vapor phase, and let's say 200 here, and you wait 1,000,000 years and it's still 100 and still 200, you have reached a state of equilibrium where the vapor pressure is no longer changing because the amount of molecules in the gas phase is no longer changing. The word equal here doesn't mean you have equal amounts of liquid and gas. What it means is that as a liquid particle turns into a vapor, one of the vapor particles turns into liquid. The forward rate equals the reverse rate, causing the same amount of vapor in the atmosphere or in this container. That is called equilibrium. Okay. So what I'm going to do for you right now is I'm going to draw a phase diagram for water. Okay, let's start with the axis. In order to change the phase of water, you have to heat it up. So temperature will be on this side. Okay, so let's start at 0 degrees Celsius. This is going to be degrees Celsius. This will be 0. This will be 100. and this will be 200. Okay, so as you know, as you learned also from the previous lectures, that the phase doesn't only depend on the temperature, but it also depends on the pressure. And we will use the units of ATM, or atmospheres. Let's start with what happens at 1 ATM. Because at 1 ATM at sea level, this is what we normally see. Water will boil at 100 degrees and 1 ATM. This is the boiling point of water. Okay, when water boils, this is what must occur. We have a container. We have air molecules pushing down on the water. Let's say that's 1 ATM of atmospheric pressure. In order for the water to boil, you must have also 1 ATM of water vapor pressure. They have to be equal or greater. The water vapor has to be equal or greater to the atmospheric pressure. This is 1 ATM of water vapor. And this is 1 ATM of atmospheric pressure. Atmospheres, N2 and O2, and other gases. Okay, that happens if you have 100 degrees Celsius underneath it. Now, if you increase the pressure, let's say we're going up 2 ATM to 3 ATM. Let's say over here, if you increase the pressure, let's draw another picture here. Let's say you have 1, 2, 3, 4, double the amount or a whole lot of water, atmospheric pressure. Let's say you're at 3 ATM. ATM. You're going to need equal amount of water vapor pressure. Let's say you're going to need 3 ATM, right? To do that, you have to get it hotter than 100 for it to boil. Let's say you have it at 200, or let's say 180. Okay. Oh, actually, let's go 200 so we have more room over here. I'm just making up these numbers, but you need a higher temperature to give more vapor pressure. So let's say it's right here. 200 something. So as you increase in pressure, you have to heat up the water more and more to get it to boil because there's too much pressure pushing down on it. Now, if you decrease the pressure, let's say you're at below 1 ATM, let's say 0.5 ATM, you don't need that much water vapor to counteract that 0.5 ATM. Therefore, the water doesn't have to be that hot for it to boil, let's say 50 degrees. So at 50 degrees Celsius right here, you don't have to have at 0.5 ATM, it'll start boiling at 50 degrees. So you're going to have a line that goes like this. These are all the different boiling points of water. Because there's so many different boiling points, this one at 1 ATM, we're going to call that the normal boiling point. Okay, so in this line, the liquid, let me just use a different color, the liquid turns into gas. Okay, at this line, liquid and gas coexist at equilibrium. They're both there together. At the line, also, the vapor or the phase change occurs. If this is going from liquid to gas, it's called boiling or vaporization, same thing. And then from gas to liquid, it's called condensing. Okay, that's the line for boiling and condensing. Okay, let's go ahead and talk about the solid. So I'm going to use a different color, maybe pink. Okay, so normally at 1 ATM, water freezes at 0. So this is called the normal freezing point. Okay, so let's go ahead and see what happens if you increase the pressure. The problem with water is if you've ever put a water bottle in the freezer, you can notice that the water bottle gets bigger or it expands. The reason is the water molecules, this is H2O, hydrogen bonds with the other water molecule, hydrogen bonds with the other water molecule, hydrogen bonds with the other water molecule. And as it freezes, it creates a hole in the middle. So the water expands as it freezes. So what happens is this. If you apply too much pressure, if you apply too much pressure, water cannot freeze. It can't freeze. Okay? Since it can't freeze, you have to get it colder than 0. So to get it to freeze, you have to get it colder. So at 3 atm, there's too much pressure and it won't freeze. So why don't you make it colder like that? As a result, these are all the freezing points of water. So this is solid on this side. And then this is supposed to be at 1 atm, you heat it up, it melts, you heat it up, it's now liquid, you heat it up, it starts to boil over here. Okay? So this line right here is where all the freezing points occur, and also the melting point, because those two happen at the same temperature, freezing and melting. Okay, and also at this line, both solid and liquid coexist at equilibrium. Okay. One more thing here. This point right here is when solid, liquid, and gas coexist. Solid, liquid, gas coexist. That is called the triple point. That's called triple point. Next, last thing is if you go up here to about 374 degrees, so way out here. Let's say this is 374. This is the T critical temperature of water. Okay, at this point, at this temperature, water will always be a gas, and you cannot squeeze it and make it into a liquid. No matter how much pressure you give it, it's always going to be a gas. It's so hot that you can no longer liquefy water even if you add pressure. Okay, so this is the phase diagram for water.